Hello everyone, I am D. Harita. In this video we are going to learn about the implementation of B-trees, insertion operation and deletion operation. B-tree is a special type of self-balancing search tree in which each node can contain more than one key and can have more than two children. B-tree is a specialized M-way tree that can be widely used for disk access. Properties of B-tree: all the leaves are at same level for each node X, that is each node contain more than one key and the keys are stored in increasing order. A B-tree of order M can have at most of M minus 1 keys and it can have at most of M children. Every node in a B-tree except the root node, it can have at most M children and definitely it should have a minimum of M by 2 children. The root has at least 2 children and contains a minimum of 1 key. Node declaration for a B-tree. So maximum is 4 and minimum is 2, as each node contains multiple keys. So taking the value as an array with size 5, count, and even each node can have a maximum of 5 children. So link also an array of size 5. Creating a new node. So create node is a function to create a new node with val and child. B-tree node of new node equal to new B-tree node. So whenever we are creating a new node, first inserting the value at position 1. So new node of val 1 equal to value 1 and the count will be 1. Link of 0 is towards root and link of 1 towards child. Placing the value in the appropriate position. This is a function to create a new node and now this is a function to add the value to the existing node. So function is add value to node. Int j equal to node of count, that is the current count is stored in j, while j is greater than position. Node of value of j plus 1 equal to node of value of j, that is moving the value from j to j plus 1, moving to right. Similarly link also, now inserting the value at j plus 1. The new value is added at node of value of j plus 1 equal to val and link of j plus 1 is equal to child. Now increment the count of that particular node. Insertion operation. Insertions are always done at the leaf node level. First step is to traverse the B tree in order to find the appropriate leaf node at which the value can be inserted. If the leaf node contains less than m minus 1 keys, then insert the element in the increasing order of the existing node. Else if the leaf node contains m minus 1 keys, that is if that particular leaf node is full, then we have to follow these steps. Insert the new element in the increasing order of element. First insert that element into that node, then split the node into two nodes at the median. So after splitting the node, push the median element up to its parent node. So even if the parent node also contains m minus 1 number of keys, that is even if that parent node is also full, again then perform the split operation by following the same steps. Here is a function for split the node. So split node into median and j. If position is greater than min, then median equal to minimum plus 1, that is median equal to 3, else median equal to 2. Now creating a new node. Whenever we are splitting a node, the elements are moved into the new node, right, and the median is pushed to the already existing parent node. So first create a new node equal to B3 node, j equal to median plus 1, while j less than or equal to max. Here we are moving the values from the existing node to the new node. So new node of value j minus median equal to value of j. So moving from the node to the new node and node of count is equal to median. Here we are going to move the values which are before the median and after the median into the new node, and now new node of count equal to max minus median. If position is less than or equal to minimum, then we are going to add the value to node, else we are going to add the value to node at position minus median. Now p-val equal to node value of node of count, that is p-value is nothing but the count of the newly added node. Now new node of link 0 equal to new node of link of node of count and count minus minus. Here is a function for sets the value in the node, that is traversing the tree for the value to be inserted, whether the value to be inserted in the existing node or if the node is full we have to split the node. First int position if of not node, that is if the value to be inserted is not in the existing node then return 1. Otherwise if the value is less than node of value of 1, that is if the value we have to insert is less than the value at position 1, then position to be inserted is 0. Else for position equal to node of count and value is less than node of value of position and position greater than 1, here we are performing a check to where to insert the value in that particular node. If value equal to node of value, then that means that already that value is existing in the particular node, so it is going to display the statement of duplicates not allowed. And if the set value in node, if node of count is less than max, then directly add the value to that particular existing node. Otherwise else you have to split the node and return 1. Insert value in B tree. So insertion function int flag and I, flag equal to set value in node. So we are going to get the value of flag from set value in node. So flag value will be 1 if not node, that is if the value to be inserted is not in the current node, then it is we have to create a new node, so it will be going to return 1. So if 1, then you have to create a node, or in the case of split node also it is going to return a value of 1, so it has to create a node. Otherwise if the flag is 0, that is we have to add to the already existing node. So this is the insertion function of inserting values into the B tree. Deletion operation. Deletion is also performed on the leaf nodes. First locate the leaf node. If there are more than m by 2 keys in the leaf node, then delete the desired key from the node. If the leaf node does not contain m by 2 keys, then complete the keys by taking the element from either left or right sibling. If the left sibling contains more than m by 2 elements, then push its largest element to its parent and move the intervening element to the node where the key is deleted. If the right sibling contains more than m by 2 elements, then push its smallest element to the parent and move the intervening element down to the node where the key is deleted. If neither of the siblings contain more than m by 2 elements, then we have to create a new leaf node by joining the two leaf nodes and the intervening element to the parent node. If the parent is left with less than m by 2 nodes, then apply the above process on the parent node also. First is copy successor for the value to be deleted. So here is a copy successor function. So after copying the successor, then we will be removing that successor element from the tree. Then remove the value from the given node and rearranging the values in the node. So remove val function int I equal to position plus 1 while I is less than or equal to count. We are moving the values towards left, that is my node of value I minus 1 equal to value of I. So moving from I to I minus 1 position, similarly links also, and decrementing the count. Shifts value from parent to right child. This is a case where if the right sibling is having more than m by 2 keys, then this is a function to be performed, do right shift. So int j equal to x of count. So while j greater than 0, then value of j plus 1 equal to value of j, that is moving from j to j plus 1. Now x value of 1 equal to my node of val position. Now x of link equal to x of link of 0, that is moving to parent, then count plus plus. Now x equal to my node of link position minus 1 Now my node value of position equal to x value of x of count and count minus minus. Through this entire function we will be moving the smallest element of the child. So the smallest element will be at one position. So x of value of 1 will be moved to the parent node. Then the intervening element will be moved to the key node. Shifts value from parent to left child, that is in case of if left sibling is having more than m by 2 elements, then we will be moving the maximum element of the node to the parent. So here is the same thing. So B3 node x of count plus plus, and if x of value of count is my node of value position. Now x equal to my node of position, x of my node of value of position is equal to x of value of 1, and we are going to find the last value using the loop. Maximum value will be at the last position in the node. So using this loop we are going to find the maximum value, then we will be moving it to the parent. So here is the function for merge nodes. This is a case when both the siblings have less than m by 2 keys, then the two nodes are merged into a single node. Here B3 node x1 and x2 are two nodes. Okay, we will be merging these two nodes into a single node of x2. So x2 of count plus plus x2 of value count equal to my node of value position, while j less than or equal to x1 of count. Right, here I am taking one more node called my node. I am moving the values of x2 to my node. Then after that I am moving the values from my node and x1 to x2. So if j is equal to position, now while j is less than my node of count, then moving the values from here. So j plus plus my node of count minus minus free of x1. That is, here I am merging x1 and x2 to x2 and removing the x1 node. Now here is the function adjust node. Adjust the given node, that is after deleting a key from the node, if it is m by 2, then it has to perform some shifts. So which one it has to perform, we are going to check using this adjust node, and we are going to adjust that particular node after performing the deletion of key from that node. If my node of link of count is greater than minimum, then you have to do left shift. Okay, link of 1 will be having more than minimum. The count is more than minimum, that is if it is having more than 2, then you are going to perform a left shift. Otherwise we have to perform a merge nodes, that is if both the nodes are having less than minimum, then merge nodes. Else, that is if of position, if my node of count is not equal to position, then again checking for the condition, if position minus 1 of count is greater than minimum, then perform a right shift, else perform a left shift. If both are not, then perform the merge nodes. Now delete the value from the node. So deleting value from a node. So first value, if value is less than my node of value of 1, then position will be 0 and flag will be 0. Else for position of my node, here we are going to get the position and we are going to set the flag value as 1. That is, if we are going to find the value in that particular node, then flag value is equal to 1, else flag equal to 0. If of flag, that is if the value is found, then my node of link of position minus 1. First step what we have to do is we have to copy successor, then flag equal to delete value from node. So now if flag equal to 0, then given data is not present, else we have to perform the remove value, that is using this remove value function. Else flag equal to delete value from node, or we have to, after deleting the value, then we have to check for the adjustments in the node using adjust node and return flag. Now deleting a value from the entire B tree. So if of not delete value from node, that is if the delete value from node returns 0, then that means the given value is not present. Else if it is present, then my node of count equal to 0. Now my node is stored in temporary node, so my node equal to my node of link of 0, and we are freeing the temp, and now root equal to my node. So this is regarding the deletion operation from the B trees. Thank you.